Welcome to This Explainer. Today, we're diving straight into what I like to call the ultimate boss fight of modern IoT infrastructure, and that is managing the massive data influx. We figured out how to build the networks, we know how to deploy the sensors, but now we have to figure out what to do with the absolute avalanche of information those devices generate every single second. Here is our agenda for mapping out the edge data lifecycle today. First, the IoT data tsunami. Second, transient storage in TSDBs. Third, filtering and event processing. Fourth, the power of predictive analytics. And finally, fog versus cloud computing. Let's get right into it. Section 1. The IoT data tsunami and the impending network collapse. Let's start with the sheer scale of the problem we face if we try to route all raw data directly to the cloud. It's incredibly easy to think of the cloud as this infinite digital dumping ground, right? But reality is constrained by simple physics and networking economics. By 2025, IoT devices are on track to generate roughly 80 zettabytes of data annually. Let that number really sink in for a second. 80 zettabytes. If you attempted to send all that raw, unfiltered telemetry directly up to the cloud, it would be an absolute disaster. It's literally enough to bankrupt a company in bandwidth costs alone in just a matter of days, and your entire network architecture would just buckle under the weight of it. So the million-dollar question is, how do we prevent total network collapse from this massive data tsunami? We obviously can't just stop collecting data, right? That's the entire point of having an IoT network in the first place. And that brings us to the ultimate bouncer of your network, the fog layer. This intermediary layer sits right between the edge devices and the cloud, and it's specifically designed to intercept and manage the data exactly where it's created. Moving on to Section 2, transient storage and TSDBs, holding the data at the edge. Because when that data first hits the fog gateway, it immediately runs into a serious hardware problem: highly limited SSD space. Think about it. You absolutely cannot store 10 years of historical data on some ruggedized street corner router. It just won't work. So, fog computing utilizes what we call transient storage to only hold what is immediately necessary. We implement a strict time to live or TTL period. You might keep the data for just, say, 7 days before it's automatically purged. It acts as a revolving door for recent context, not a permanent digital archive. And this limitation perfectly illustrates why standard relational SQL databases just won't cut it here. SQL is fantastic for deep, complex queries, but it completely chokes on the sheer velocity of IoT data. Instead, we rely on time series databases, or TSDBs, like InfluxDB. These are purpose-built to swallow thousands of time-stamped sensor readings every single second without missing a beat. All right, Section 3, filtering and event processing, aggregating the noise. Now that we've temporarily stored this raw data, we have to aggressively filter it. We have to filter it so we aren't sending 18 million identical temperature readings to the cloud. If a room is sitting at exactly 72 degrees for 5 hours straight, transmitting every single second of that stability is nothing but wasted bandwidth. This is where complex event processing, or CEP, steps in as our ultimate filter. A CEP engine evaluates endless data streams in real time against strict rule sets. So instead of forwarding every single tiny blip, the fog node steps in and says, hey, let's just take the average temperature over the last 5 minutes and only send that single number to the cloud. We can actually quantify this massive networking save using a really handy metric called the data reduction ratio. It's a simple but absolutely vital formula measuring our raw data volume against the remaining filtered volume. By running this calculation, we get a crystal clear percentage of the bandwidth, and let's be honest, the money that we just saved. And the results of this filtering? They are truly staggering. By turning a 1000 Hz stream into a simple 5-minute average, the fog achieves a 99.99% reduction. That is conserving massive amounts of bandwidth. We've literally saved the network from total collapse, all while perfectly preserving the core informational value that the cloud actually cares about. Now for Section 4, power of predictive analytics, real-time machine learning at the edge. This is arguably the most critical and honestly the most exciting capability of the fog layer. This is where local processing power steps up to do way more than just filter data. It actually starts thinking. You see, analytics generally falls into 3 main buckets. Descriptive tells you what happened in the past, predictive tells you what is going to happen in the future, and prescriptive tells you exactly what you should do about it right now. While the cloud is undeniably great at historical descriptive analytics, looking at years of data to find broad trends, the fog is the absolute master of predictive and prescriptive analytics in real time. Let's look at a high-stakes, real-world scenario to make this concrete. Imagine an offshore wind turbine. Inside that turbine's massive gearbox, sensors track minute vibrations and temperature changes, streaming this raw data 1,000 times a second straight into a machine learning model sitting on a gateway right at the base of the tower. Because this ML processing is happening locally, it spots anomalies instantly. It detects a tiny flutter in a vibration frequency indicating a ball bearing is going to shatter in exactly 45 minutes. The gateway doesn't wait to ask the cloud for permission. It executes a prescriptive command immediately. It safely feathers the blades, applies the brakes, and shuts the entire system down. Only after the crisis is totally averted does it send a tiny 2-kilobyte alert to the cloud to dispatch a maintenance crew. The crucial takeaway here is that waiting for cloud latency would have resulted in a totally destroyed turbine, proving the immense financial value of edge analytics. If that 1,000 hertz stream had to be batched, transmitted over a wide area network, stored, and then analyzed by a distant server, well, the bearing would have shattered before the shutdown signal ever made it back. A $200,000 failure was prevented purely by eliminating network latency. Section 5. Fog versus cloud computing. The ultimate cheat sheet. Let's synthesize everything we've learned to really lock down your understanding of the entire system. It really comes down to using the exact right digital tool for the exact right phase of the data's life. When you contrast the fast, raw, real-time fog layer against the massive historical cloud, you see they form this perfectly complementary ecosystem. At the edge, storage is transient and databases are time series based to handle massive, raw data volumes with latencies under 10 milliseconds. But once that fog layer filters out the noise, the cloud takes over. It uses persistent storage and relational SQL databases to run deep historical analytics on that aggregated, clean data. So the fog acts as the ultimate data bouncer, passing only highly valuable insights up the chain. But there is a catch. Decentralizing all this processing power introduces terrifying new vulnerabilities. If a hacker compromises that wind turbine's local gateway, they don't just steal data. They take physical control of the brakes on a multi-million-dollar machine. As we push intelligence further to the edge to save our networks, we have to ask ourselves, are we sacrificing our physical safety for digital speed?